Till now we have seen about continuous, so whether a function is continuous over a range or not. Now if we don't have any holes or jumps in a function, we said that the function is continuous. Now let's look at what is differentiability. So coming to differentiability, here we need to know whether the function is smooth or not. So what do I mean by smooth or not is, if you look at this function, if you see this is definitely continuous. If you say from here to here, it is definitely continuous, right, over this range. And also if you see the way it is moving, it is smooth, right? But if you look at this one with a sharp edge, it is also continuous, right? But then it is not smooth. So how to find out whether it is smooth or not is, we are going to use a concept called as differentiability. So differentiability or derivative. So let's talk about derivative. So what is derivative of a slope of a function at a point is, if you are going to draw a tangent for that, let me draw one more. If you are going to draw a tangent, let's say this is the point. If you are going to draw the tangent for the function at that point, okay, now the slope of this particular, let's say this is the x-axis. If you say this angle is theta, then tan theta is nothing but the slope of the tangent for the function at this point, right? Now this one is also called as derivative. So what is the derivative of a function at a given point is, try to find out the tangent, and then you find out the this tan theta. After writing out this tangent, you find out tan theta, that is nothing but the slope of it. Now the slope of the tangent is also called as the derivative, right? So a function will be smooth only when you have a unique tangent, right? And also it is going to have a finite value. So it should exist as well as it should be finite. Then only we can say that it is smooth. Otherwise it is not going to be smooth. For example, if you look at this point, right? Now for this one, at this point, if you ask me to draw a tangent, I can draw infinite number of tangents, right? So even this one is going to be a tangent. Any line passing through that is going to be a tangent, right? Therefore, even though the tangent is existing, they are not unique. So we can say that it is not smooth. Therefore, coming to differentiability, a function is said to be differentiable if it is going to be one, continuous, which means it should not have any holes or it should not have any jumps, and second point is there should not be any corner edges, right? So what do I mean by corner edge? Means a sharp edge like this, right? If it doesn't have it, we can say that whatever I told you just now is informal definition, right? So what is formal definition at this point is, see this. Now when can you say that the tangent is going to be unique for a function is, if you can see just to a point to the left of it, right? And if we can find out the tangent there, and if we can draw a tangent to the right of it, just to a point to the right of it, if all these tangents are same, then we can say that it is going to be unique. Otherwise we can draw infinite number, right? For example, if you see this point, if I draw tangent to just a point left of it, it is going to be this line, isn't it? If I draw tangent at a point to the just right of it, it is going to be this line, right? Therefore you are going to get many tangents there. So if the left side tangent and the right side tangent, and if the point at that point, if the tangent all of them are same, then we can say that it is differentiable or the point function is smooth. So whatever I said just now is informal way. Now let's look at the formal definition. Let's see this. Let f of x be a real valued function on an open interval a comma b, and there is a point c which belongs to this function, which means we are having a function which is defined over a comma b, and we are talking about a point which is between a and b, right? Then f of x is said to be differentiable or derivable at x equal to c if limit x tends to c, f of x minus f of c divided by x minus c exists, and if it is finite. So what is the meaning of this one is, what they are trying to say by this expression is, let us say this is the function, and assume that this is a point on the function. Let's call it as c comma f of c, right? And let us assume that there is one more point which is a moving point. Let's say this is x comma f of x, right? Now how can we draw a tangent to a curve? Now if you look at this chord, as this point moves towards this point, now that chord will become the tangent. Are you getting this? As this point move towards this point, so as I slowly move this, it is going to be like this. See, as I slowly move this, finally it is going to be a tangent. Got it? So as I move this point x close to C, whatever I get, that is nothing but the tangent, right? And now if you look at this line, the slope of this line is going to be y2 minus y1 divided by x2 minus x1, isn't it? So that is what is written, f of x minus f of c, y2 minus y1 divided by x2 minus x1. Now when is it going to be the slope of the tangent? So it is going to be slope of the tangent only when x is approaching close to c, which means as I move this point x towards this point c. So if you want to understand what accents here, let us say this is f of x and this is x-axis, right? So as I move this point x towards this point c, right, now that this line will become the slope, the tangent, and the slope of that line is going to be the slope of the tangent, which is nothing but the derivative, right? So see this one. So as I move this point x towards c, the slope of this line will become the slope of the tangent, right? Now if it exists and if it is finite, we can say that it is differentiable or derivable. This is one definition. Let's see one more definition also. Okay, one more is this limit is derivative. This limit is derivative of f of x and it is denoted by f dash of c. So sometimes we can also write it as f dash of c, like this. Whatever this limit is, we can also write it as f dash of c. Okay, now one way of checking whether the function is derivable or not is the other way. See this, look at this condition. Now this condition is saying that necessary and sufficient conditions for a function to be derivable at a point is existence of the finite left hand derivative and finite right hand derivative and equality of both of them. So what we are trying to say by this point is, if you want to see that there is a unique tangent for a line, now let us say at a point C, just try to find out the tangent to a point to the right of it and to a point bit left of it. Now if all these three tangents are going to be same, or all of them are going to have almost the same slope, then we can say that it is going to have a unique tangent at that point with the unique slope, right? So that is the meaning of it, which means left side derivative and right side derivative, both of them have to be equal, right? So what is left hand derivative is, see this. Now if you are talking about a point C, we know that this is the slope of the tangent as x approaches c minus. So which means if you are talking about, let us say here there is a curve and here there is x, okay, now here there is c, right? Now we shall take a point to the left of c and we'll try to move this line, this point towards c minus. As we are moving this side, it is nothing but the slope of the tangent which is drawn at this point, isn't it? That is the meaning of it. So just move x towards c minus. Now whatever line you are going to get, that is nothing but the tangent drawn at this line, and whatever is the slope is nothing but the slope of the tangent to a point left of it. Now what about the other side? Okay, so this is nothing but moving this means c minus means we can substitute, we can subtract a small number h and we can substitute over there, right? In place of x, you can substitute a small point. So see this. So c minus h. So what is that I am trying to do is, from c I am subtracting a small value so that it will move to the bit left. Got it? And here also from c I can substitute a small value and I can write it, which means c. X minus c, what we are trying to do is, from c I can subtract a small value and I can write it there, which is nothing but c minus h minus c. So which is going to give us minus h. Got it? Okay. Now similarly right hand derivative also works the same way. So what is it? We have to move the point x to a point just to the right of c. So that is why I am writing c plus h, right? So if you write c plus, now this is nothing but the slope of the tangent drawn at a point just to the right of c. Okay, now that can also be done by writing in place of x c plus h. So which means I am just adding a small value to c so that it will move to a point to the right of it. Now that value is close to 0, right? Whatever value you are writing is close to 0. Here also whatever value you are writing is close to 0, right? Now you are going to add that h to c, and in the denominator also you are going to put, c plus h. Then you are going to get h here. Got it? F of x is differentiable at x if these two are equal. So one way to solve, see, this is one definition. Earlier whatever definition we have seen here, this is one definition. Using this we can find out whether a function is differentiable or not, but it is a bit difficult to do it this way, and in most of the questions we are going to use this method because it is simple and it is easy to find out these two, right? Finding out whether a value is unique or not, it requires we need to find all the values, right? But instead of that, if we can find these two values and if they are equal, we can say that it is differentiable at that point. Got it? Okay.